Hello everybody, hope that you're doing well today. It's going to be a great day today. We're going to be talking about axions, and in particular, we're going to be talking about axions. Now, I know what you're saying. You're saying, yeah, but we talk about axions all the time, and that's true. We do talk about axions quite a bit, and that's because axions are near and dear to everybody's heart. But in this case, we're going to go into a little bit more detail on some of the experiments about axions, and as a consequence, it's going to be that much more awesomer. All right. Okay, so standard disclaimer, most of this is coming from memory. Some of it's coming from experience, but even that's in my memories. And so the discussion that will take place, to the best of my knowledge, is what's going on in terms of axions and axion dark matter. So for axions, we need to start back in the day with an important story, and that is the story of the QCD Lagrangian. QCD Lagrangian. Let's see if it actually has a picture of the QCD Lagrangian. I don't know if it will. So, okay, here's the Lagrangian. This is the QCD Lagrangian, and it's missing one of the things that I needed to find. So I will just describe what I'm talking about when it comes to the QCD Lagrangian by bringing up the drawing pad. And positioning the drawing pad such that it looks like it fills the whole screen when in fact it doesn't. All right, now, one good question to ask is, what is the Lagrangian and why do physicists always talk about it? It's like, oh, the Lagrangian, write down the Lagrangian, and then like all the world will be a better place. So the Lagrangian is a way of encapsulating the energy, the different forms of energy that a system has. In general, so the Lagrangian is given by the letter L for Lagrangian, which is one of the few instances where the letter actually corresponds to the name of the thing that you're writing about or that you're discussing, as opposed to angular momentum that's also given by L, but this is Lagrangian, which is given by L. Sometimes it's given by script L. Lagrangian is the difference between the kinetic energy and the potential energy in a system. So you have the kinetic energy and the potential energy in a system, and the Lagrangian just contains that information. It's the difference between these two. This is different than the Hamiltonian. The Hamiltonian, which in general, Hamiltonian H is the kinetic energy plus the potential energy. It's like the total energy of the system is the Hamiltonian, but we're not talking about the Hamiltonian, we're talking about the Lagrangian. So what the Lagrangian actually does is it's a way of containing information such that you're able to produce the behavior of matter by looking at the behavior of the Lagrangian across some trajectory. Like if you have an object here and an object here, and you want to find out how is my object, I'm sorry, not an object. If you have a location, so this is a location and an instant in time over here, and another location and instant in time over here, and you want a particle to go from this location over to this location, the Lagrangian contains the information that you need in order to discover what path will that thing take, what path does that particle take as it goes from one place in time to another place in time. And it's related to how much that particle, how much of the Lagrangian the particle has, let's see, it depends upon the difference between the kinetic and the potential energy of the particle throughout its trajectory. So it might start off with some kinetic energy, it's going to go through a field, some kind of force field, and that's going to adjust its potential energy. And then the kinetic energy and potential energy are going to readjust until you arrive at the final destination. And in particular, a system will tend towards the path that minimizes the Lagrangian, which means that it maximizes the potential energy. So as a particle moves from one point in space and time to another point in space and time, it tries to maximize the potential energy, or in other words, minimize the Lagrangian along the way. And so here's an example of how that works. So suppose that you take an object right here and you throw it up into the air, and it's going to follow a path that looks like this. Okay, so this would be just kind of generic projectile motion with no air resistance under the force of gravity. And so what's going to happen is it's going to come up here, and it's going to, when it has the most potential energy, it's going to go the slowest. It's got the most potential energy, and it tries to spend as much time up there as possible. So it moves very slowly when it's got a lot of potential energy, and when it starts to lose potential energy, then it picks up speed and shifts that energy back to the kinetic energy. So as you go from one place in space and time to another place in space and time, the trajectory that's followed by particles in nature is one that keeps it in the high potential energy state as long as possible. So the Lagrangian is the kinetic energy minus the potential energy. It tries to stay in this area as long as possible. And what happens is you take this Lagrangian and you integrate it over time between this point and this point, and then you try, that's called the action, and you try to minimize the action, which is minimizing the Lagrangian at every point in time. And so there you go. That's how the Lagrangian works. It keeps track of all the different kind of interactions because there are a variety of interactions that contribute to the potential energy. You could have the electromagnetic force that contributes to the potential energy. You have charges over here, charges over here. You could have a gravitational force that contributes to the potential energy. So you've got this would be big G m over r squared, or over r not squared because it's a potential energy. You could have the strong nuclear force, you could have the weak nuclear force. They're all going to contribute into this potential energy because those are all force fields that affect the potential energy that a particle has at a given point in space if it interacts with all those things. Okay, so when you write down the Lagrangian specifically for the strong nuclear force, specifically from the strong nuclear force, I'm not a minor celebrity, I'm a major celebrity on my channel. But that's about it. On my channel, I'm the celebrity. But yes, I am a physics professor at the University of Nevada, Las Vegas, and I do mostly astronomy stuff. And so here we go. The QCD Lagrangian has a term in it. So here's the Lagrangian, and they're going to write it with a script because it's a Lagrange density and blah, blah, blah. It has a bunch of parameters in it. You set it equal to, and then you have a bunch of terms in it. And one of the terms in particular has a quantity called theta, and then it's got some matrices and other terms in here, but this thing is the thing that's important right here. So, and this term is the term that is important for our discussion. This term is Q, is a CP violating term. Okay, so there is a term in the QCD Lagrangian. So this is Lagrangian, I'll change this, QCD, this is a C. The QCD Lagrangian has a term in it, and that term is a term that gives you the violation of charge parity conjugation in the strong force. So what CP violation means that if you take a system, physical system, and you switch all the electric charges, and then you run it in a mirror. So you take all the particles in a system, you look at it in a mirror, remap all those particles to their reflections in the mirror, switch all the electric charges, and then let the physics of the system run. The overwhelming majority of interactions and behavior that we see, you get exactly the same results. So you switch all the electric charges, and then you run it in the mirror world, and the physics is basically the same. However, we know that there are some systems that violate this transformation. There are some systems that violate charge parity. So charge, switch the electric charges, parity, switch it in the mirror world so that the right hand becomes the left hand and vice versa. So there are some small number of interactions that we know violate charge parity conjugation. And this is important because if it weren't for CP violation, then we wouldn't be here. We never would have formed because CP violation is essential to producing the asymmetry between matter and antimatter. And if that asymmetry did not exist between matter and antimatter, it's a very small level, 1 part per billion. But if that violation did not exist, or the difference did not exist between matter and antimatter, then there would never be galaxies that formed. You would never form, you couldn't make anything out of matter because it would have all annihilated in the early universe. So in terms of, so a question is, what is S, the action S in the QCD Lagrangian, what physical property does it represent? It doesn't represent a physical property, it represents the behavior of the system throughout a trajectory from one point in time to another point in time. So the action, the action is the integral of the Lagrangian over time. It tells you basically across the trajectory in time, from one point in time to another point in time, what is the relationship or what is the difference between the kinetic and the potential energy. And so it doesn't represent anything physically, it's an accumulation of mathematical properties of a system as it evolves, subject to the different forces that are acting on it. I don't think there's any, it's a fundamental property. Action is a fundamental property. It actually, so this integral of Lagrangian over time, has units of energy times time, which means it has units of h bar or Planck's constant. So h bar is Planck's constant, that is a fundamental constant in the universe. And this is basically a unit of phase space. So maybe a way to think about it is like this. So h bar is a unit of phase space. You have a direction here, and that direction, so you have a direction x, you also have a momentum x that is in a different direction, has different units and everything, and then you have another direction y and a momentum y, and you have a direction z and a momentum z, and you have a momentum t, which is energy and the time coordinate. And so that gives you every interaction that takes place in space-time is actually takes place in a phase space volume of what, 8? Is that 8 dimensions? So 3 spatial dimensions and a time dimension, and then their respective momenta that go along with that. So that's a phase space, is the fact that you can have a position in some direction and you can have motion in that same direction. So what happens when you integrate? You have the action that is the integral of the Lagrangian over time. You're integrating the difference between the potential and the kinetic energy across the phase space. And so basically minimizing the action, what does that do? Does that minimize? I'd have to think about it. I have to spend a couple hours brooding over what that means fundamentally. But I think minimizing the action means that you're minimizing the phase space volume that the system travels through. I believe that's what that means, that you have some trajectory and you're mapping out the phase space that you would like to follow. And there are other trajectories that one could imagine taking, but they take up a larger phase space volume. Like this goes through a larger volume in phase space as it goes from one place to another. And so what you do is you say, I'm going to integrate this up to the end, and then I'm going to divide by my unit of phase space, which is Planck's constant. And that relationship tells me how many fundamental volumes of phase space I have traveled through as I go from one place to another. And the minimum volume that I travel through is the system that is the trajectory that a system will follow in the real world, like in the universe. Okay, we're going to go with that. I'll have to think if that's how close that actually maps to reality, but that's basically what it represents. Okay, back to the QCD Lagrangian. So the QCD Lagrangian has this term in it. QCD has this term with a theta in it, and then there's other terms. And this is a CP violating term. So it's important because if it weren't for CP violation, we wouldn't exist. So then what you do, what experimentalists would want to do, this happened in the late 1960s, early 1970s, is we knew that this theta property or theta parameter is part of allowed interactions with the strong nuclear force. So QCD means the strong nuclear force. So this is quarks, leptons, it's quarks and gluons. So this is interactions between quarks and gluons. It should have this interaction that's available to it with this property theta. And if theta is non-zero, so it's greater than 0, or like the absolute value is greater than 0, then you would expect, that's the strength of the CP violating portion of the strong force. And it would produce a dipole moment in the magnetic field of the neutron. So you have a neutron here, and what it would do is it would mean that the neutron it acts like a small magnet. The neutron has a small magnetic dipole moment. And so what you do is you go and you measure the neutron magnetic dipole moment. I'm pretty sure it's the neutron magnetic dipole moment. You go out and you measure it, and you would expect, you measure it and you get some number, and you'd expect this to be something like of order 1, like some number relative to the other parameters that you have in here. There's probably some H bars and some C's and stuff like that. And you would expect this to be of order 1, this parameter out front. And the answer that you get is that this theta parameter is no larger than, so theta is no larger than, so it has to be less than 10 to the minus 10. And this is a small number. It is much, 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 much smaller than 1. So if you were to just randomly pick a number between, it doesn't have to be exactly 1, it could be like between 0 and 10. Randomly picking a number between 0 and 10, and you get 1/1 as the number that you choose. That is smaller than what makes people comfortable. So this makes people uncomfortable. They would say 10 to the minus 10, we expected like pi, or we expected e, or we expected the square root of 2. And instead we got 1/10 billionth, smaller than 1/10 billionth. And so this forced particle physicists to re-examine what does it actually mean, what is this QCD Lagrangian, and why is there no CP violation in the strong force? This measurement says that the strong force interactions, the interactions between gluons and quarks, does not violate charge and parity conjugation. So if you take an ensemble of gluons and quarks and you take their reflection and you switch the electric charges, then you get the same interaction to better than a part per 10 billion. And that is, so the strong force basically has no CP violation, and that's a problem. It basically means that for some reason, there has to be some mechanism, either amazing fine-tuningness, like the universe just chose to position this thing, the dial that it could turn, like the universe can choose whatever it wants for this parameter, and it happened to choose the position on the dial that is good to within 10 decimal places of some value. Or maybe this theta is identically equal to 0, so maybe it's exactly equal to 0. For some reason, the universe like declared that it has to be equal to 0. Or there's some mechanism that drives it to 0, and so its expectation value is 0, but it might be a slight deviation from non-zero simply because maybe there's quantum fluctuations that move it away from 0. So it's either definitively equal to 0 because the universe chose for it to be 0, or it there's some physics that pushes it towards 0, and it's just been staying there ever since. Okay, so those are the choices. Either physics drives it to 0 or the universe declares it to be 0. Okay, that then brings in the question, how do you get it to behave this way? It turns out that one of those solutions is preferred over another. Physicists don't like to declare, even though this thing is allowed, the universe chose not to allow it, or chose not to exhibit it. The physicists prefer some physical explanation for why something is 0. So if that term is allowed in the Lagrangian, the fact that you could have a system where theta is allowed to be any number, the fact that it could be any number, that's a B, by the way, and it chose to be a number that is 0.000000 or less than that, physicists don't really like the idea of, well, the universe just made it 0 and therefore it's not there. They prefer having some physical explanation for why it got small. And the physics explanation that they came up with is as follows: that this parameter is actually not just a number. It's not a universal constant that the universe chose, but instead it represents a new particle. And so this is a new particle. And as a consequence of it being a new particle, it has an equilibrium. So this particle, it's a field. So there's a new field, kind of like the electromagnetic field, and it has an equilibrium. And the equilibrium, so the expectation value, so this is the equilibrium. This says equilibrium. The expectation value, its equilibrium value is equal to 0. And then you can have fluctuations on it, and the fluctuation of this field, that is a new particle. So if you cause this field to wiggle up and down, you get new particles coming out of it, and that is called the axion. Okay, so it's similar to saying, I have a new field, it's like a new string connected between 2 points. It has an equilibrium oscillation of 0. So this would be if you just leave it alone, it's going to come to equilibrium and it'll be like that. And then if I start plucking the string, it's going to start shaking, and the vibrations, I call them phonons, or like sound waves. And phonons are individual sound waves propagating along this vibrating string. The same thing's going on here. You have a new field, it's like a new string set across there. Its expectation value is 0, and so that theta value that you would measure in these experiments is the vacuum expectation value of 0. And if you pluck the string, you get vibrations in it, and that vibration, this in quantum mechanics, this is a particle wave duality. So the vibrations on the string are the particles, and that is called the axion. And what this does is it allows the CP problem to be explained away through some physical mechanism. And it cleans up the strong CP problem. And so I've shown this before, and I'll show it again because it's an important part of the memorabilia that I can have in my office. It was named after the Axion dishwasher detergent, because it cleans. See, this cleans. The Axion detergent cleans up your dishes. Axion, the particle, cleans up the strong CP problem. Now, Axion is not available in the United States anymore, but you can still get it in Mexico, at least as of 2010. So there you go. Axion was named after the dishwasher detergent because it cleaned up the strong CP problem. Okay, now we have a new particle. We have a new particle, and so any self-respecting physicist would say, okay, let's go look for this particle. How do you look for the Axion? So now we have the Axion, and we have some constraints on the behavior of the Axion. It turns out that the, let me switch this real quick. I need to open this up again. It turns out because the Axion is related to the strong nuclear force, the properties of the Axion are related to the particles exchanged around in the nucleus. It's a strong nuclear force thing, and so its properties are coupled in with the strong nuclear force. The particles in the nucleus that mediate the strong nuclear force between the nucleons, like fundamentally it's quarks and gluons, but between the nucleons it's actually pions. And so the properties of the Axion are related to the properties of pions. These are these subatomic particles that bounce around inside the nucleus and keep the nucleus bound together. Okay, so, but we don't know, all we know is that there's a relationship between the Axion. We don't know, we can't pin it down to what its properties are directly. So what we have is the mass of the Axion here, and we have the coupling, it's given by G, of the Axion here. So the strength of the coupling of the Axion and the mass of the Axion are related to each other and related to the same property with the pion. And what that looks like is a band of acceptable values for the coupling of the Axion and the mass of the Axion. So if the mass of the Axion is big, then it must have a stronger coupling. If the mass of the Axion is small, then it must have a weaker coupling. Okay, and that coupling is a coupling to photons. So this is G is the coupling of the Axion to photons. Like, how does it couple to light? And that relationship is related to the properties of the pion. So that's the important thing. The Axion couples to light, and the relationship between the mass of the Axion and the strength of the coupling has to land in this band. If it doesn't land in this band, then it's not able to explain the problem we came up with in the strong nuclear force. It's not able to explain what we observe with the strong nuclear force. Okay, so what does that mean? We have a coupling to photons. Okay, we can do that. We can create photons in a laboratory, and we can use those photons that we create in the laboratory to discover or constrain the properties of the Axion. Okay, if you have a particle that has similar behavior but does not have couplings in this band. So pretend that the universe invented a new particle that had a coupling to photons and had a mass and behaved otherwise like the Axion, but did not solve the strong CP problem. So say the universe said, I want a particle to have these properties right here. This would be called an Axion-like particle. This is called, like in general, it's called the QCD Axion. So if you have an Axion like that, if you have an Axion that solves the strong CP problem, then it's a QCD Axion. If you have an Axion, like an Axion-like particle that does not solve the strong CP problem, then it's called an Axion-like particle or a generic Axion, lowercase Axion. Okay, so that sets the experimental stage. We can look for a particle that couples to photons that can solve the strong CP problem. All right, how can we build an experiment around this? What this means is we can have a particle like this. Here's an Axion that comes in, and it can split into two photons. Okay, or you can have a photon come in like this that couples to another photon from some outside source that converts into an Axion. So you can produce an Axion by scattering photons off of each other. So you take a photon coming in, you have an ambient source of photons, and you scatter them off of each other and produce Axions with some probability. Okay, well, Axions themselves have very, very, very very, very, very weak couplings to other things. And so let's say that you put a wall here. You have a wall made out of bricks. You sit it right here. And then the axion can pass through that wall without any trouble. Okay, now you have basically a beam of pure axions coming through here. You can start with a beam of photons coming in. Some of the photons will convert into axions, some of them won't. Those that do convert into axions will pass through whatever material you put in the way. So now you have a beam of pure axions coming out the other side, and then you can do the process in reverse and produce photons from this beam of axions. So this is a light shining through wall type experiment. You basically send in, the idea here then is that you send in a beam of particles. You send in, not a beam of particles, you send in a beam of light. Here's a beam of light coming in. It's got really super bright, so you have all sorts of photons coming around in here. You choose the energy of the photon specifically so that there's not a wide range of energies that you have in your beam. So you have a laser beam, basically is what that means. So instead of just a bright source, you have a laser beam so that you have very specific energy of the photons going in. It's easier to characterize what's happening. So you have this beam of light coming in. You have an ambient magnetic field. So this is a magnetic field. Magnetic field, that says magnetic field. You have this magnetic field, and that magnetic field is a supply of photons. And then it converts, you'll have these incoming photons. So here's laser. This is a laser. It hits these photons in the magnetic field and converts and produces a beam of axions. Then you put a blocker in here, you put a wall of some sort. The beam of axions makes it through the wall. You have another magnet over here so this has a magnetic field with photons in it, and you look for these axions to rescatter and reconvert back into photons on the other side, and you put a detector on this side. Photons are magnetic. So the photons interacting magnetically, a magnetic field is an ensemble of photons from the electromagnetic field. And so when there's an interaction with a magnetic field, it's because of the exchange of photons. So it's not that they're magnetic the same way that iron is magnetic. It's that the magnetic field is the electromagnetic field, and as a consequence, it's photons. The magnetic field is made of photons. Okay, so let me show you an example of what this looks like. You can't detect the axions directly, you can't detect the axions directly because we don't have an axion detector. It's a lot easier to make a detector that detects photons. It's way easier to make light detectors, right? Our eyes are light detectors, cameras are light detectors, radio frequency cavities are light detectors, photomultiplier tubes are light detectors. But axion detectors themselves, I mean, how do you interpret that interaction? Somehow along the way, you still have to convert it into an electrical signal one way or the other. So if you have an axion detector, you have to generate an electrical signal in order to record it on a computer, right? You have to convert it to a voltage on a meter. You have to convert it to some kind of electric current that flows. And that's what your eyes do, right? You have photons. Photons come into your eye. They excite things in your retina that sends an electrical signal to your brain, and then you interpret it. The same thing would go on here, that you have to somehow convert it into an electrical signal because all of our detectors run off of electricity. You can imagine having a detector that runs off of gravity, for example. So if the magnetic field is made of photons, what is the wavelength? The wavelength is all wavelengths. So a magnetic field has all wavelengths of light in it. They're all virtual particles because they don't turn into real particles until there's an actual interaction that takes place. But it basically has all wavelengths in it. So if you want to detect an axion, somehow you have to it has to interact with some kind of force that moves something or wiggles something or excites something or twists something. It has to exert some force on some object that you can convert into an electrical signal. And the easiest one to do is just to convert it into the electrical signal through the coupling with photons directly. Okay, so let me pull up. Do axions interact with any other subatomic particles? Not that we know of. So the QCD axion basically only interacts with the magnetic field. And I guess the quarks and gluons to some extent. But in terms of like what we can detect in a detector on the outside, far from the nucleus, it's only photons that they're expected to interact with. So let me pull up the original experiment to do this light shining through wall thing. Let me pull this up. The original experiment was called the BFRT experiment. So that's the Brookhaven, Fermilab, Rochester Trieste. This is dark light. That's a different one. Here is, oh, this is looking for something else. So here's the BFRT experiment. I actually want the actual results from the BFRT experiment. This was done in the early 1990s. BFRT experiment, Brookhaven, Axion. Let's see. None of these things are showing it. Why is it results? I don't know where they published it. It was probably in, let me go to Wiki and see if I can find the thing here. BFRT. No. I mean, this is an important result. This is like one of the first searches for Axions, and there's nothing in it. I don't remember what year it was in the 1990s. We'll just put 1990 and see what happens. Well, this is just silly. Okay, here we go. Brookhaven National Laboratory and the University of Florida. Okay, here's what I'm going to do. I'm going to go to GAMEV. And we're going to go to our results, experimental results with links. Light shining through wall experiment. Proposed experiment to do light to take a pseudo BFRT. Okay, here we go. Photon regeneration. I think it's this one, 1992. Here's the link. Fermi National Accelerator Laboratory right there. So Rochester, Brookhaven, Fermilab, and Trieste. There we go. So this is their experimental results submitted to physical review letters. And this is from the Fermilab library. So we'll scroll down and we'll see what this what their setup was. They should have a diagram. Here's the explaining the physics of what's going on. Here's the coupling that they're looking for. It's a coupling, this coupling right here. This coupling constant, there's a 5-parameter, and then this electric field and magnetic field. So the magnetic field in your magnet and the electric field, the stronger the electric field or the stronger the magnetic field gives you a stronger coupling to the Axion. So you want to have a really strong magnetic field. They should have a diagram. I got 14 more pages to go, or 7 more pages to go. There's no diagram shown right here. That's terrible. Okay, here is the coupling that they're looking for. Photon comes in. This is from their laser beam. Here's the photon from the laser beam. Here is the coupling to the photon from the magnetic field. It's in quotation marks because it's a virtual particle in the magnetic field, and that's where the Axion production happens. And here is their experimental setup. Okay, and they did some clever stuff here in this experiment. First of all, they had a fairly strong magnetic field. It was 3.7 Tesla. 3.7 Tesla magnetic field. That's I don't know where they got the magnet from in terms of like, this was a magnet that was used in a particle accelerator of some sort from Brookhaven National Lab. So Brookhaven National Lab, it's on Long Island. They have a variety of particle accelerators. One of the biggest one there now is the relativistic heavy ion collider, where they're looking at what happens in the really, really early universe. How do quarks and gluons behave in the very early universe? In this case, they had some magnet. It was related to some particle accelerator, so it was 4.4 meters long. You have a 4-meter long magnet. It's at 3.7 Tesla, which is quite a bit if you're going to have a magnet. They want the magnet. The magnet needs to be polarized. So you can't just have a generic magnetic field. It has to be a magnetic field in a particular direction. So it's a dipole magnet, meaning that it has a north pole and a south pole. A dipole magnetic field, it's got a north pole and a south pole, and the magnetic field is really uniform throughout the volume of the magnet. And then what they did, and this was kind of cool. So they have this laser beam, 514 nanometers. It's got some number of watts that tells them the number of photons that go through. And they had it in what's called a, what's it called? It's a cavity. So what's going on here is that they bounce, it's in a cavity that has a bunch of mirrors, and they bounce the photons multiple times in this cavity. So the laser beam comes in, bounces off the back, bounces off the front, bounces off the back again, bounces off the front again. I think it's an optical delay line is what it's called. I believe it's called an optical delay line. So it has a mirror in it. If you look at the mirror at the back end, you send the light in through a small aperture at the front end, and then the back mirror, the light will hit a series of spots. So you aim the light in a particular direction, and it comes in and it bounces off one of these things, comes back, bounces off a curved mirror, and then that reflection goes to the next spot, and then it comes back and bounces off this one, bounces off the next one, bounces back in, and then it goes around, works its way around like that, and then eventually makes it back out the hole that you sent it in. So you send it in the hole, it bounces back and forth in this optical delay line. It's not a resonant cavity. That's a different thing. It's not like LIGO. LIGO has a resonant cavity in its arms. This is an optical, I think it's an optical delay line is the correct term, but I can't remember. It's been too long since I've talked about it. Anyways, it bounces back and forth multiple times and then comes back out. You maybe get like 20 or 30 different bounces. You can go, depending on how much you want the spots to be able to overlap, you can have a lot of bounces. But what this does is it increases their sensitivity by quite a bit, right? Because now instead of having a single laser beam that comes in, you get multiple tries at converting the photons to axions, right? This is a very, 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 very rare process. And so the more tries you get at getting the laser beam to convert into an axion, the better. And then you just have, then there's your brick wall, and then on the far side you have the other magnetic field, and it converts those axions. They have a lens to focus it onto their photomultiplier tube. So you have a 4 meter cavity here, 4 meter cavity here. They're basically two magnets from the same accelerator that they're using. They have this optical chamber where the light bounces multiple times on one side in order to try to produce axions as much as possible. And then they have, in the far cavity, the axions reconverting into photons being focused onto their photomultiplier tube. And then there you go. So that's the setup of the Brookhaven, the BFRT experiment, Brookhaven, Fermilab, Rochester, and Trieste. And so, they make these measurements, they have accounts, and then they say, like, we're going to subtract off the signal that we already know is going to be there. There's like some ambient signal that they can detect because there's thermal excitations of their photomultiplier tube or whatever. And then they can say, okay, we know that this is the systematic effect, we subtract that, and it turns out that you get basically nothing, right? The signal is consistent with 0. So they didn't see anything in their first try. And so here you go. This is the experimental region. I talked about, here's the coupling to the axion mass, and here is the axion mass itself in electron volts in this case. That's how they measure it. These are the QCD axion models. So this band right here is the QCD axion models. And this light shining through wall experiment was able to go right here and exclude this region. There's some particle physics experiment that preclude the axion below, like the axion cannot have coupling stronger than this amount because it would cause certain violations of something that they detect in particle detectors. So that's excluded from particle accelerators. This thing excluded by the solar model, that's a different experiment that I will be talking about either today or some other time. That's the CAST experiment, probably some other time. And then the BFRT experiment right here, this is the thing that's excluded. Now you may wonder, like, why did they do it if the solar model already excludes that? And there are a variety of reasons. One is you want to have two different, it's good to have two different experiments that test it using different assumptions or different experimental setups. And so anyways, there's reasons to do that. So excluded by this experiment. Now, one of the things about this is you'll notice that the sensitivity declines and you get these weird peaks in the sensitivity. Like it's sensitive in this area and then all of a sudden it's not sensitive anymore, right? The limit's way up here in this little gap. And then it's sensitive again, then not sensitive again. Then it's sensitive again, then not sensitive again. And that is actually related to the geometry of the magnets. So if you have a magnet, so here's the magnet that you're going to produce the axions in. So here's your magnetic field like this. And the probability of detecting an axion is going to be related to how much time it spends in the magnetic field. And then, but you also have the issue that the axion can reconvert into photons. So you can have this wave function come in. Here's a photon coming in. It starts to mix with the axion field and have some probability of turning into an axion at different distances in here. So the probability of detecting an axion or producing an axion is going to grow. But then you have the reconversion process that starts to take over, and it declines again. And if you have very specific couplings, you can start to produce, like, you can develop the probability of having an axion appear. But then by the end of the chamber, if the chamber is a particular length, then that probability goes back to 0. So the probability basically grows over time and then shrinks back down again. Okay? Or you could imagine, and so if you have a magnetic field that happens to be that length, so it's the strength of the magnetic field and the length of the magnetic field that matter. So you can, if you increase the strength, then the oscillation happens more quickly. This is very similar to neutrino oscillations. But the probability of the axion being produced grows over time, and then it will shrink back down, and then it will grow again on the other, if the magnetic field was longer. And so you could imagine a case where maybe the axion, the probability grows and then shrinks, goes through 0, and then grows again and goes back through 0. You would just write this as an oscillation like that. So you have all these different wavelengths. You can have 3 bumps in it or 4 bumps in it. And you can have some number of cycles that the axion will convert inside your magnetic field. And the probability of detecting the axion is 0 going in because it's a pure photon coming in. And the probability of detecting an axion by the time you get to the end is also 0 because it's gone through so many cycles of switching between an axion and a proton inside the magnetic field. Okay, so the oscillation length is related to the length and the strength of the magnetic field. Okay, and so what that means is if you are unlucky, you're unlucky and you choose a magnetic field of a given length, and it just so happens that the axion that you detect, the axion that maybe the universe has in real life, coincides with this length of maximum insensitivity, then you're out of luck. Like, I'm sorry, you picked a magnet, it's the wrong length, and it's invisible. Axions are invisible to you as a consequence. That is what's going on here with these different dips that they see, is that the axion could live in this gap where it just happened to not be sensitive. So that's one issue that you run into when you have a fixed length magnetic field. Okay, so fast forward, gosh, like 12 years. This was 1992, fast forward to like 2004. And there was an experiment that was run in, whatever that place is called, Italy. So I haven't got to the point where this could be a dark matter candidate. I guess I should say it up front. The axion, if it exists, because it has mass and it has very weak coupling to all the other standard model forces, it could be the dark matter. So axions were initially invoked as a way of explaining the strong CP problem, but because it's a particle that could exist and have mass, it's also a candidate for dark matter. And how much dark matter depends on a number of things. So back to there's an experiment, PVLAS experiment. Okay, so the PVLAS experiment was an experiment that was done in the early 2000s, about 10 to 15 years after the BFRT experiment. So this Brookhaven experiment where they were looking for the axion using these magnets and lasers and stuff. So this experiment was looking for axion or effects of axions using a different effect. Basically, can you have different kind of optical behavior of the vacuum? So they're looking at these different couplings. Here's like particle production can produce dichroism or birefringence. And so they get all these things, and it turns out that they saw a signal. They set up an experiment and they saw a signal. So it's the same idea. They have a magnetic field, they have a laser. They're looking for the interaction of the laser light with the magnetic field, and particles that can produce an effect here would be like the axion. So now there was an experiment, in answering your question, there was an experiment recently where they were looking at, it was a big dark matter detector, and they saw a signal that was consistent with axions coming from the sun. And if that's the case, then that particular axion is way outside of the realm where this experiment would be sensitive. Either of these experiments would be sensitive. The axion there was, I already got rid of the exclusion limit, or like the plot where the axions were, so I can draw it again. So there was an experiment recently that showed a signal consistent with axions coming from the sun. However, if you look at this figure with the coupling here and the mass here, and then here's the allowed axion band, all the stuff that we're talking about, or that I'm talking about, is like down here. Like here's the solar model stuff, and here's like collider things, and it goes up like this. The stuff that was seen in that dark matter detector, here's the laser experiments, right? This is the BFRT experiment is right here. This is the band of allowed axion properties, and what they saw was like way out here, like really high mass axions. But it's the results that they got from that experiment could be explained by a number of other things, and so axions is kind of the last resort. Even though it's the most exciting result, if they see it, it's by far the most exciting result. But it's also the result of last resort. If it's the most exciting result, it means that before you get excited, you have to go and exclude all of the other possibilities. You have to exclude the tritium explanation and so forth. Okay, so they're looking for these things, and it turns out that in this Italian experiment, they saw a result. Let's see if they show what their signal looks like. Here's their signal. Here's their experimental setup, and not seeing the signal, not showing up here, how they calibrated everything. All right, so that was no help. All right, so let's go with Gamev, Cho et al. 2008, because that one actually shows up. That is not the one that we're looking for. Here we go. This is the one we're looking for, 2007. And here's me right here, right there. Okay, so this experiment that they found, this Italian experiment, saw a signal. They saw a signal for an axion, and it looks like this. The allowed signal that they saw, it turns out when they rebuilt the experiment that they weren't able to reproduce the result. But at the time, they didn't have to reproduce the result, they just barely got it. So the BFRT experiment, this one that was from Brookhaven, here's the exclusion limit that they had, and it has this, these are the places where they're not sensitive, like these gaps in kind of the orange background, or the tan background. So that's where they're not sensitive, because in that case, if the axion has those couplings, if the axion has these couplings and is this mass, then they would disappear at the end of the magnet, and so you wouldn't see any in the detector. So that was the sensitivity of the BFRT experiment, and the results from this Italian experiment that came 12 years later, the signal was right here. The band of allowed signals from the PVLAS experiment went right through the place where the BFRT experiment was not sensitive. So if the PVLAS experiment turned out to be a real signal, then the experiment from 10 years earlier was the most unlucky experiment in the history of the world, because they built an experiment, they were totally sensitive to whatever it could have been. They were sensitive to everything in this region, except that the magnetic field length that they had rendered them insensitive right at the mass where the PVLAS result found a signal. So it'd be, if the PVLAS result was real, they would have won the Nobel Prize, and these guys would have missed it by a decade, simply because their magnet was 4 meters long. So anyways, there's that. Okay, so when this result came out in 2006, early 2006, late 2005, something like that, when this PVLAS result came out, it sparked a new interest in looking for these axion signals, because it happened to be that the signal that they found was in a gap where we already knew we were capable of making instruments sensitive enough to see that. What that basically meant was you could just pick a magnet of a different length, run exactly the same experiment, and you should pick this signal up. Yeah, if it's a real signal, you just pick a different length for the magnet, and you run it again, and you pick the signal up. That was what happened in the mid to late 2000s, where a number of groups around the world, like a half a dozen groups. There was a group at DAISY in Germany. There was a group in Italy. There was a group, like the group at Fermilab. A variety of groups from all over the place. There was one at CERN. Started looking for these axions. Because the technology, the capability was already demonstrated 20 years earlier. At this point, it was roughly 20 years earlier where the technology was demonstrated. And so it was fairly easy to just, you're at a national laboratory, there's a bunch of magnets sitting around, you might as well build it. Okay, so that's what we did at Fermilab, is that we built a replication of the same experiment, except that we designed our experiment so that we would be sensitive in the region where the previous experiment was not sensitive. So the previous experiment was not sensitive at this particular mass, and we designed our experiment so that we would be sensitive at that particular mass. But we run into the same problem. At Fermilab, the magnets that you use at Fermilab are 6 meters long. So we have a 6 meter long magnet, and we're going to run into the same issue that if the axion happens to live in this such that when you produce the axions on one end, they disappear by the time they get to the other end. And so we had to come up with a way, like, how do we deal with this? Like, how do we change the magnetic field length so that we're sensitive everywhere and not just at that end? Thank you for that, Raid. I appreciate that very much. And here's how we solved that. What we did is we had a magnet. Here's our magnet. And we have a brick wall. We have a wall that we need to have in that magnet so that we produce axions on one side. The axions are blocked, or the photons are blocked by the wall, and the axions can make it through the wall. And then we have a detector on the far side. So we have magnetic field on both sides. And we have, these are all electromagnets. All these magnets are electromagnets. So I can describe where that comes from in a little bit. So the magnet from the Brookhaven National Laboratory was an electromagnet from an accelerator there. The magnet that we used was an electromagnet that was a spare for the Tevatron, the big particle collider at Fermilab. So we had our wall in the middle. That we divided our magnetic field into two regions that were basically 3 meters each. Because it's a 6 meter long magnet, 21 feet is the actual length. And it's 3 meters, so we have basically 3 meters on a side, and we have the wall in here. Our wall was a mirror. We chose a mirror because then what we can do is send the laser beam in, bounce it off the mirror, bring it back out, and we can measure the power, measure the total amount of energy, like the number of photons that have come in. So we can calibrate our laser by just measuring the power output as it bounces off this mirror, because the overwhelming majority of the particles are going to bounce off the mirror and come back. And only a tiny fraction, if there are axions, only a tiny fraction will convert into axion and come to the other side. But then here's the clever thing. The clever thing was, and it wasn't me that came up with this, it was another experimentalist that came up with this. It's actually an experimentalist who wasn't even on the experiment at the end. So he wasn't an author on this, but he listened to our presentation and he's like, oh, what you could do is this. And he explained it and we were like, yeah, we could do that. And so we did. And what it was is it was a plunger. So we have this magnetic field and we have our mirror connected to a plunger that we can slide in and out so that we could adjust it and operate in two different modes. One was with the mirror in the center of the magnetic field. So we have 3 meters on one side and 3 meters on the other. And the other way to operate it is to have the mirror on this side so that we had basically 4 meters on one side and 2 meters on the other. And that difference between those two, thank you for those subs, I appreciate that very much. By changing the length of the magnetic fields, it means that we change where we're sensitive and insensitive. So when you combine, we operate in two different modes with the reflector in the center and then with the reflector at one end. And so we get two different sensitivity curves. One of them is this red one. Okay, the red dotted line. Red dotted line here. And then the other one is this blue dotted line. Okay, and it's got two different lengths, so it has two different regions of insensitivity, one for the 4 meter and then one for the 2 meter, basically. It's the combination of everything that matters. Anyway, so together we have one region where we still have a region of insensitivity from one configuration, but it's covered by the other configuration. And that was the big breakthrough. It was that, okay, we have a magnet, we're going to set up an experiment where we can adjust the relative lengths of the production side magnetic field and the regeneration side of the magnetic field, where you produce the axions and then where you regenerate the photons. And we can adjust the length so that we're sensitive everywhere. And that gave us ultimately this curve here, the black curve. And so for a while, we were the world record holder. Our collaboration was the world record holder for constraints on these axion-like particles that were missed by the BFRT experiment and detected by the PVLAS experiment. It turned out that it was some systematic effect because they weren't able to reproduce it. But nevertheless, this sparked a huge race to do more axion experiments at laboratories. And there was one last breakthrough that came through fairly recently, and that is a really interesting breakthrough. So this was 2007 when we ran the experiment, and 2008 when the paper came out. The person who suggested the plunger use, I think he got, I think it was in the acknowledgments. Did he show up in here? No, he doesn't show up in there either. He got a pat on the back. That's basically what it came down to. Anyways, he wasn't particularly interested in participating in the experiment, but he was like, it's one of those things where a passing comment, hey, why don't you just do something like this? No, so no one has detected, so this signal was not confirmed. The PVLAS signal was not confirmed. And no signal has been seen in any similar experiment that's come from this. However, one thing that it spawned a new interest, and in particular, it spawned new interest on the theory side. So that a number of theorists came along and started saying, what are some other ways? We haven't thought about this for 10 years because, things have been ruled out. What are some other ways that we could look for axions? And then there was a really clever paper that came out by Pierre Sakivi at the University of Florida. And his suggestion was as follows. So if you remember from the Brookhaven experiment, they set up this optical delay line where the light came in and bounced back and forth some number of times. I don't remember the number of times that it was, but it was some number of times, bounced back and forth between the two mirrors. And that gave them, say 20 different passages in order to, how do I pronounce archive? I pronounce it archive. So the archive where these things are stored, that's just what I say. And that's what almost all my friends say it that way. I wouldn't associate with someone who said it differently. But anyways, that's how we all say it. Early on, when that preprint server came out, so that would have been like the late 90s, the astronomers call it AstroPH. So this archive thing, it has different listservs, depending upon whether you're doing high energy physics, or if you're doing astrophysics or condensed matter physics. So it has all these things. And of course, all the astronomers only care about astrophysics, and so they call it AstroPH. Because astro for physics. But there's HEP pH, and there's a bunch of different high energy physics ones, but I just call it archive. And then of course, everyone else has to jump on and copy us. It was originally high energy physics primarily, and then mathematics got into it and quantum physics. And so now there's a bunch of stuff. There's like biology, look at all these things, economics, there's like SciPH or PhiPH, which is like psychology preprint server. So there's a number of other preprint servers that followed the model of the particle physicists because they're always behind. They're always behind the physicists. Never forget that. Okay, like here you go, med archive and bio archive. Oh, they capitalized the R. That makes it even more silly. All right, so if we go back to, this was the Brookhaven experiment where they bounced the light back and forth some number of times in order to give more opportunities to produce the axions, and then they had the detector volume over here. And then here was Pierre Sakivi's insight. It was Pierre Sakivi and Carl van Bibber, who was at Lawrence Livermore National Laboratory and is now at I don't know if he's still, he may have retired, but he was at the Naval War College. And what they said was, you can do even better. You can do better if instead of having a delay line where you have the beam bouncing back and forth between there, if you set up what's called a Fabry-Perot cavity. Fab with an F. So that would be Fabry-Perot cavity. Okay, so these are the optical cavities similar to what you have in LIGO. And the idea with a Fabry-Perot cavity is that you send in laser beam through a mirror. So you have a mirror that's like 99% reflective, which means that most of the light bounces back off the mirror. 99% of the light bounces back off the mirror. But the 1% of the light that makes it in is now trapped. Trapped, and it can't escape. And so then you have another mirror over here that is going to be like, say, 99.9%. So it's even more reflective. And so the light comes in, some fraction of that light gets trapped inside, and then it bounces back and forth and back and forth and back and forth. And you design the cavity so that it reinforces itself. so that as these things bounce back and forth, they come in with the same mode. You have to have exactly the same wavelength. You have to have a well-conditioned laser beam, so that the wavelength of light is uniform, that the shape, the profile of the beam is uniform, so that as it bounces back and forth, the reflected beam doesn't cancel with the incoming beam. So you have an incoming beam of light and you have a reflected beam of light coming off the far side, and you want them to recombine here when you hit the near mirror. So like your laser's on this side. When the reflected beam hits this mirror, it has exactly the same footprint. It's got exactly the same phase. Everything lines up so that the new light that comes in adds to the light that's bouncing around in there. Because if it comes in out of phase, then it cancels and it fails. But if you bring it in so that it comes in phase with exactly the same footprint, then you build up a huge amount of power inside here. The quality factor of that, 99% reflective at the wavelength of the laser. You don't care about any other light because you're sending in a single wavelength of light, and so it only needs to reflect at that light. So in a lot of cases, these Fabry Pro cavities, you can actually see through the mirror, except at the specific wavelength of the laser beam that they're using, which in most cases, it's 1024 nanometers. So the idea is you have a Fabry Pro cavity, and you send the light in, it builds up a huge amount of power. I mean, you can do like hundreds of kilowatts. 100 kilowatts is a lot, but you can do kilowatts of power going in here. And that means that you have a huge amount of circulating energy going in through here. Hundreds of times or even thousands of times more energy than the laser beam itself. So with the cavity, the delay line cavity that they had in the BFRT experiment, it bounced around 20 times, so you get a factor of 20 improvement. This is a factor of thousands or tens of thousands improvement by having this Fabry Pro cavity. And then what you can do is, now you produce these axions. So here's an axion that makes it out of that system, goes through the wall of one form or another that basically prevents any stray photons from making it through. You don't want any stray photons in the other cavity. You only want axions, because any stray photons is fake signal, like and other news sources. Okay, so then what you do is you set up a second cavity on the far side, and you set it up as an optical cavity as well. The same kind of Fabry Pro cavity, so that when the axion comes in, it's going to produce a photon, and the photon that comes into this cavity is then going to bounce, it's going to be trapped inside this thing, and it's a resonant cavity, and it's going to be driving this cavity at the resonance frequency, which is going to amplify the signal that you get out of it. So you amplify the production of the axions by building up energy in a resonant cavity. The photons come in, and the cavity gets the electric field, the electromagnetic field in that cavity gets excited because you're driving it at exactly the right frequency. It's got the right wavelength, it's got the right shape, latitudinal or profile, like the cross-sectional profile of the beam is exactly the right shape. And so when you're bringing new photons in, you're driving the cavity at the harmonic frequency where it likes to oscillate. And so you build up a huge amount of power. Just like pushing someone in a swing, if you do it in phase, the amplitude of the swing gets really big. Here you have a cavity set up so that an electromagnetic field that's in there will drive to very large amplitudes, which is what you want. That's big circulating power. Okay, the same thing happens over here. You have another optical cavity such that any excitation of the electromagnetic field in here is going to bounce back and forth and drive that cavity at its response frequency, the same way as like pushing someone on a swing. So the challenge is that this optical cavity and this optical cavity have to be coupled together. They have to be coupled together so that they resonate at exactly the same frequency, because any photon that you produce in this cavity is going to be a photon that came from this beam, and so it has to match the properties of this cavity have to match the properties of this cavity exactly in order to drive this resonance. And so what you do, it was really quite impressive. The theory that goes into it is relatively straightforward, but it's clever in that you're producing them in a cavity that's resonating, and so it's got huge amplitude in the electromagnetic field, like lots of photons bouncing around in there. And then you're driving the detection cavity at the frequency that it likes to respond, and so you get a big response. And that drastically improves your sensitivity to new axions with the technical challenge. That you have to have these two cavities so that they resonate at exactly the same frequency with each other. And the way that you do that is that you have it oscillating. You can have a secondary beam come in here, like a green photon. So if this oscillates at 1024 nanometers, you can send in a secondary beam at like 532 nanometers. Like one way to do that is you have a secondary beam at 532 nanometers, and if this cavity resonates at 1 micron, 1024 nanometers, it will also resonate at 532 nanometers because you have just twice the number of wavelengths. But it's a different it's a different frequency, and so you can couple these two cavities together using one wavelength of light and know that they're behaving the way that you want them to, and then your signal is at a different wavelength of light that is a multiple of your calibration wavelength. So that's pretty cool. 1024, 532. You're right. That is 512. So what's going on? Why am I missing this? 1060. Oh, it's 1064. It's 1064 nanometers. I apologize. It is not 2 to the 10th. It's not 1 kilobyte. It is 1064 nanometers. Wow, I've been saying that wrong for a while now to all my physics majors. Oh well. Sucks to be them. All right, so 1064 nanometer wavelength light, and you double it to 532 nanometers. So this is a neodymium YAG laser, and this is a frequency doubled neodymium YAG laser. Anyway, so you can get these two cavities. You know that they're responding to each other at the right frequency, and you can verify that with a wavelength that is different from the wavelength that you're sending your signal in. And so that was pretty cool. So this experiment is currently being run out of an experiment based on this design. So we started designing an experiment based on this design at Fermilab, and eventually we got kind of distracted and went on to something else. There is another group at DAISY. So DAISY is the Deutschland Elektronen Synchrotronen something or other. So it's the particle accelerator, the equivalent of Fermilab except in Hamburg, Germany. They're doing one called ALPS. And I don't know the state of this one. Axion-like particle search. ALPS, and they have ALPS 2, and their ALPS 2, I believe, is a setup that's like this. It's been a while since I've been in contact with them. ALPS originally was one of these groups that started up after the PVLAS result, looking for it, and we beat them at Fermilab. And then they came along and said, okay, well, fine, we're going to do this Resonant version, and I think that's what their plans are. I don't know the current state of the ALPS 2 experiment, so I'll have to look that one up. I believe that they're, with this coupling, the Fabry-Perot coupling experiment, it gets them sensitive, like down to the point where the solar, you may recall, it's not up there anymore, but if you show this plot that looks like this, here's the Axion things, here's the coupling, and here's the mass. The BFRT and gamma and stuff was way up here, like far from the Axion stuff, far from the QCD Axion. So maybe Axion-like particle could be dark matter, but far from the QCD Axion. So it doesn't actually address the original question. And then you had this thing from solar axions that kind of cuts through like this. That's the CAST experiment. That's for a different stream. And this gap, the ALPS 2 experiment should bring them down right till they're roughly sensitive, have the same sensitivity as the solar telescope thing. And so that makes them, it's a huge change, because increasing your sensitivity in this direction is really hard to do with these light shining through wall experiments. The reason being that it's one thing to just convert and produce axions. That's one thing to do. The hard thing to do is to then reconvert it, because the same probability, the same really small probability that you have to produce the axion in the first place, it's the same small probability of taking an axion and converting it back into a photon. And so it's a small probability times a small probability. You have to both produce the axion and reproduce the photon, both with really small probabilities. And so you get enormously, like wickedly small probabilities of getting both conversions. What you have with the solar telescope is that you just say the sun already produces it, and so we only have to do the reproduction side. We don't have to reproduce the photons. The sun already produces the axions. We only have to reproduce the photons, and so we don't have two small probabilities. We only have a single small probability. And this laser-coupled cavity experiment basically says, well, we just have a really high-quality resonator, high-quality Fabry-Perot cavity, and so that gets us even though there's a small probability of producing a photon, we get a gigantic amplification of the signal, and that makes up the rest of the difference. So I can look real quick to see, there was one thing about GAMEV that I wanted to cover that I overlooked and that I shouldn't have. Let me see did I still have it up here? Whoa, that's not it. Okay, so let's go with GAMEV. Show. Oh, I can steal one of their talks. Do I want to steal one of the talks? See, here's me. Let's see. I think I might have. Okay, here we go. Let me see if I have information on this. WIMP dark matter, reasons to do it. I'll talk about that later. I'll talk about this later. And that, okay, so here's these experiments, and that's different, and this is different, and that's not what we're talking about. Okay, here we go. Here's the Axion experiment. This is what we've talked about before. You send in a laser beam, you couple it to a magnetic field, you produce an Axion, you put a brick wall in there, and you can see it. Here's the experimental setup at Fermilab. So here's the 6 meter long. Let me zoom this out. I'll make it bigger. Make it bigger and slide it over this way. Okay, so here's this 6 meter long magnet. It's a Tevatron dipole magnet. It's a spare magnet for the particle accelerator. It's on this test stand where they tested the magnets for the particle accelerator. It has a plunger and an optical box down at this end, and then this side over here, this is the laser box where the laser beam gets bounced around and put in. Now what we did is we had a really high powerful pulsed laser. Because any photodetector, so in the far side down here in this box, there's a photomultiplier tube. All photomultiplier tubes have noise. Like there's some random noise in the system and there's nothing you can really do about it. There's noise. And so, however, the noise was at roughly 20 hertz. The average was 20 hertz. There would be 20 random photons per second that were read out by the photomultiplier tube. And that's from like thermal excitations and all sorts of stuff. You can't get rid of noise. But what you could do, 20 hertz, is you have 0.05 seconds basically between adjacent noise photons. And that seems like a small amount, 0.05 seconds. But you can build laser beams where the pulse of the laser, the light coming out of the laser, is only 5 nanoseconds wide. 5 nanoseconds is 5 billionths of a second, not 500ths of a second. So it's like 10 million times narrower than the gap. So you have these photons that are coming in, like noise photons that are coming in, and you can squeeze an entire laser pulse into the gap between noise photons. So we had a pulse laser, and we were timing, or we would only accept as signal any photons that landed in our window. And so let's see. And so this is what it looks like. So we ran 4 different polarizations. What's shown on this, so these are the actual arrival times of individual photons in our detector. Let me make it really big so it's more amazinger. Okay, so these are the arrival times of individual photons in our detector, and they are almost certainly all noise photons that come from electrons scattering around and stuff like that. So this is what the noise photons look like relative to the laser pulse in nanoseconds. Now this is after 5 hours of running. So this is the accumulated number of things that arrived in our detector in a window, a 100 nanosecond wide window near the center of our laser pulses. So here's our laser pulses. Here you can see what we did was we set up a whole series of reflective mirrors, and we sent the laser pulse in, and most of it gets reflected off of each mirror. And we got it down to the point where basically half a photon would make it through a series of mirrors to see our detector. Because a single laser pulse, with this laser, it was a 5 watt laser, something like that. 3 watt, I think it was 3 watts in the green. So you have 3 watts of power concentrated. That doesn't sound very bright. You know, we have like 100 watt light bulbs in our houses, but it's 3 watts of power concentrated into 20 5 nanosecond pulses, which means that the instantaneous power, so you're taking all that energy and you're focusing it down into things, the instantaneous power in a single laser pulse was like megajoules, or like megajoules per second, which is, if this laser beam were to hit you in the eye, so here's your eye and the laser beam comes in and hits it, it would like burn a hole in the back of your retina and cauterize it faster than you can blink. It's a 5 nanosecond pulse, and it's got huge energy concentrated in that 5 nanosecond pulse. And so that is, you don't want to have this anywhere near your eyeballs. So you have to be real careful when you're working with high-powered lasers, and that's what we had here. And certainly a photomultiplier tube that's sensitive to individual photons would get blasted to smithereens by these laser pulses. And so how do you calibrate your system if you can't actually hit it with the thing that you want to calibrate? And the answer is that you shine the laser beam in, you have a bunch of reflective mirrors, nothing is 100% reflective, and so you lose 99%, and then another 99%, and then another 99%. And so you're using the mirrors as a filter to get you down to basically a half a photon per arrival. And so we counted a few thousand photons arriving at a given instant in time, relative to the laser pulse. So we could measure the light travel time from one side of the experiment to the other side of the experiment. And you operate it for several hours, you build up this thing, and now we know what's our window. So then what we could say is, here's the width of our laser pulse. That's actually the profile of the shape of the laser pulse. It's not purely Gaussian, it's got a little asymmetry to it, but that's the profile of the pulse shape. And then that says, okay, we're only going to count photons that land inside this window relative to our laser pulse. So we can time the production of the laser pulse, and we can time, and we know how long it takes to get to the detector, and we're going to limit ourselves to only pulses that land in that window. And you can see that so these are basically 5-hour runs apiece, so that's 20 hours of operation. 20 hours of operations, we detected a grand total of 4 photons in 20 hours of operation. And they are all consistent with the background noise. Right? This is the background noise, is the stuff outside of there, and the signal range is the stuff inside of there, and the amount of signal that we saw is consistent with the amount of background that we would expect. And so that's where we get our constraints from, is how many background photons do we expect to find, and how many do we see, and they were consistent with basically no excess signal. If there was an axion in this range, then there would have been, maybe hundreds or tens of photons in here, certainly a lot more than what you'd expect from the background. So now in terms of how big was this laser? So the laser itself was, you could carry it, but it was fairly big. It was about the size of, almost the size of a trombone case. So a trombone case, like a meter long-ish, and cross-sectional area about the size of my head. And then, so that was the size of the laser. It had a big, gigantic power cord that went into it, because it's got a bunch of other cabling that goes in to make sure everything functions properly. So that laser was in a box and a few mirrors to detect when was the laser produced, and detect the power meter when the light was reflected back off the center. And so that was the setup of the experiment that we had. So these were some of the early Axion experiments, at least in terms of this light shining through a wall technique. And we will see with this ALPS 2 result, let me see if ALPS 2 has any results. ALPS 2 results Axion. ALPS 2. Here's their setup. Laser beam, cavity mirror, or like a reflector, blocking, occulting device, another cavity, and then a detector on the far side. They have, whoa, look at that. Wow, that's a great result. Congratulations to them. Wow. Okay, so here is wow, that's really good. So here's the QCD Axion, this band right here. Here's the solar results that's cast right here. You can see cast barely, you can see it. It's not a very good image. So these are results from the solar experiment. That's a stream for another time. White dwarf cooling, that is also a stream for another time. But here's ALPS 1. So this is what you get. This is basically the same as what you get with GAMEV. The experiment that I was on is couplings around this. So they have sensitivity that's very similar to the sensitivity that we had in our experiment. That's with the generic light shining through wall result. Then they did the coupled cavity result. Look at that. 1, 2, 3. That's like a factor of 10,000 more sensitive. That's a huge increase in sensitivity that they got through this with this experimental setup. There's no way to do that with the generic light shining through wall setup, because you have to both produce the photon and reproduce, like produce the axion and then reproduce the photon. The improvement that you get in terms of running for longer, like why don't you just run longer, and then your sensitivity will go up. You only gain sensitivity as the eighth root of the amount of time that you spend observing. So if you observe for 8 times as long, if you want to get a factor of 2, no, I'm sorry, I lied. I think it's the fourth root. It's the fourth root of time. Okay. I'll have to look that one up. So I think I'm going to go back with the eighth root. I think it's the eighth root of time that your increase in sensitivity improves, because of the coupling, the fact that you have to produce the axions, you have to reproduce the axions, and then you have an additional square root of time in there because of statistical noise that you have in your detector. And so that means that you would have to observe for like 16 times long. Is it 16? Okay, so ignore it doesn't scale well with time. Let's just put it that way. I'll have to go back and redo the math, and I can't do it right now. So it takes a lot longer. So you can't just like observe twice as long and get twice as sensitive. It's like you observe 10 times as long and you get 20% more sensitive. It's a huge impediment to designing these experiments, is that you can't just observe for longer and do better. In fact, that makes it convenient, because then you just run for one shift. You run for 5 hours and then you're like, okay, we're done. There's no point in going to 6 hours because it doesn't make any difference at all. So if it is the eighth root, then you have to run 256 times longer. If it's the fourth root, then you only have to run like 100 times longer. 2 to the fourth is what? Is that 32? No, 2 to the fourth is 16. So you have to run 16 times longer. But I have to go back and remember how that all worked. But that's not the point. The point being that you can't just run these experiments longer. It doesn't evolve well with time. You don't improve your sensitivity with time the way that you do in most other experiments. And so switching the technologies to this coupled cavity, look at that. That's like 4 orders of magnitude improvement in the coupling that they get from that. That's amazing. And it also puts constraints on models for some of the astrophysical mysteries that are out there, like why the universe is transparent to TeV gamma rays, and why supernova gamma ray bursts results can be detected over long distances. So anyways, that's a really great result. Congratulations to the ALPS people on that. That's a huge improvement in sensitivity. So it's not ALPS 2 that was doing the sun axions into photons. That's CAST. That's the CERN Axion Solar Telescope. That's this experiment. And I'll talk about that some other time, the CAST experiment. Maybe I'll do that next time, since we're on the subject. So anyways, that is Axion results. And there you go. And their sensitivity will surpass the CAST bounds in the lower mass region. So this is ALPS 2C, which is their third run. This looks like it's only their, I don't know that they've made it all the way down that far at this point. The schematic overview of the sensitivity reach of the final stage of ALPS 2, ALPS 2C, depicted in the impact. So this is not their current result. Do they have their current result? Past experiments. There's their original setup. It looks a lot like the setup that we had. Here's their, now one thing about the DAISY, so they're using DAISY magnets, DESY magnets, and their magnets are actually curved. So the Fermilab magnets are basically straight, but their particle accelerator is curved, and so all their magnets are bent. So they have the same kind of setup with kind of 2 different plungers the way that we do. Can I make this bigger? So Hera is the name of their particle accelerator. So there's their setup. Here's their CCD camera. Here's their frequency doubling crystal. Comes in at 1024 nanometers, bounces around a bunch of times. They condition the beam And then there's their magnet. They have to limit how they put their magnet in there because their magnet's curved. So here's their results. These are actual results from their experiment on these axion-like particles. So GAMEV, BFRT is the light blue, this light blue. GAMEV is green, that's us. Well, that was me. And then their ALPS, their first run of ALPS was this red. And their goal was basically run until we beat GAMEV. And so they got 1 order of magnitude more sensitive than we were. It doesn't show their ALPS 2 results on this page. Anyways, it seems like a really cool design, and I wish them well. That's ALPS 1. I don't know. ALPS 2. Do they have results from ALPS 2? Maybe those are results. Parameters, ALPS. The last column was the approximate sensitivity gain for axion-like particle surge compared to ALPS 1. Schematic overview of the sensitivity reach of the final stage of ALPS 2 depicted in this impact. Okay, so this is expected sensitivity. I'm pretty confident. I've no doubt that they can reach the sensitivity, because this is all just technical stuff, and these are totally competent scientists. They might not reach all the way down there. Maybe it's a little bit lighter because there's some systematic effect that they don't come across. But these are all competent people who, you design an experiment, you say this is what we expect, and the things behave the way that you expect them to behave. And so, unless there's some new physics to discover, that's really cool. Anyways, congratulations to them, and I wish them well on that. And that is the initial stages of axions, and why we care about axions. Because remember, there's two. The main thing for axions was, why does the strong force not have CP violation? And the second thing is, if there are these axions that solve the strong CP problem, they might be the dark matter. They might be contributing to the dark matter. And if so, we should go detect them, because that can explain some of the mysteries of the universe.